Okay, welcome back. So now what we're going to do is we're going to talk about this square. So we're going to fill this in. And so as a result of the corollary, this is what we're looking at. So either there's either going to be a particular solution or not, right? So this is going to be yes or no. And then for the solutions, the number of solutions for the associated homogeneous system, there's either going to be one solution or there's going to be infinitely many solutions, right? So in this case here, what happens if we have a particular solution and only one solution to the associated homogeneous system? Well, what's the one solution? Well, that's going to be the zero vector. That's the only that's only one solution that you have is if you have the zero vector. Because remember, if you have one non-zero vector, at least one non-zero vector, then you have to have an infinite number of solutions to the homogeneous system. So if you have this and this, then you're only going to have one unique solution. Okay? Now, what if you have a particular solution and infinitely many of the solutions of the homogeneous system? Well, in this case here, you're going to have infinitely many solutions. And so, by the way, we're talking about general solutions here. I didn't write that down. Sorry. General solutions. Ugh. Okay, so when we're talking about general solutions, we can look at the number of solutions of the associated homogeneous system and the particular solution. So if we have one unique solution to the homogeneous system and there exists a particular solution, then you'll only have one unique general solution. If you have infinitely many solutions to the associated homogeneous system, and the particular solution exists, then you're going to have an infinite number of general solutions. Now, in the case that you don't have a particular solution, and you have a unique solution to the homogeneous system, the associated homogeneous system, which is again the zero vector, then you're going to have no solutions in the general, for the general case. No general solutions. And also, if you have an infinitely many solutions to the homogeneous system and no particular solution, right? No particular solution exists, then again, you're going to have no general solution. Now, in the top of the table, this dimension is a simpler one. Okay, so let's look at this for a moment. Okay, in this case here, we can find out this information when we perform Gauss's method on a linear system and we ignore the constants on the right side, and then we just pay attention to just the left-hand side, then we're either going to end, right? So when we do our row reduction on the left-hand side, we're either going to end up with every variable becoming a leading variable, or we're going to have variables that are not going to be leading variables. In other words, they are free, right? And so in particular, when we're dealing with, well, let's talk about the special case where we're talking about where every single variable ends up being a leading variable, right? And so in that case, we have a unique solution. Okay? One unique solution. Now, when we talk about ignoring the other side, ignoring the left-hand side, what we're basically saying is we're only dealing with the associated homogeneous system. Okay? Because again, when we ignore what's going on the right side, we're just making those zeros, right? And remember, when we're talking about the associated homogeneous system, we're dealing with zeros, and all of those will always stay zero. So we just focus on the left-hand side and doing our elementary reduction operations along the way, and we get in an echelon form. Okay. So the special case is when we have a system with the same number of equations and unknowns, and when we reduce that, we have a solution that's going to be unique if and only if every variable when it's reduced in echelon form is a leading variable. In other words, there's no free variables. And in that case, you have a unique solution. Okay? So again, when you have a system with the same number of equations and unknowns, then that system will have a solution, and that solution is going to be unique if and only if it reduces to an echelon form where every variable is a leading variable. Okay? And this is only going to happen if and only if the associated homogeneous system has a unique solution. Right here. And that's going to lead us to our next definition of when we're talking about singularity, or a matrix being, or a system being non-singular. And that we'll introduce next time.